Now let's take a look at chapter 10, which is on memory systems. When we use the word memory, we are starting to talk about something different than just digital storage. This is a big differentiation in what we've been doing. Before, we have had the ability to store a bit. Okay, we have that ability, and that has been done using a D flip-flop. This absolutely can store information. It's very synchronous, meaning that a clock comes into the system, and we grab information on every rising edge of a clock, and we store it. So Q will hold D. That is storage, okay? But when we talk about memory, we talk about storing information using a circuit that is a little bit smaller than a D flip-flop. So it's something that can store a 1 and a 0, but it's not as capable in terms of what it actually does. Because if you think about it, it wasn't just the D flip-flop, right? We started with the D flip-flop, but then we immediately started doing things like, well, you know what else we should have? We should have an enable, okay? And then we want to group them together, and we want to start adding other logic to it, and we had a reset, and everything's great, okay? Well, it turns out that it takes a lot of transistors to build something as capable as a D flip-flop. So one of the things is that if you tried to build like a large array of storage using D flip-flops, it would take tons of transistors, and you wouldn't see the density that we actually see in modern memory systems. So what happens is that you move to, this is going to be called sequential storage, and it's really in the form of registers. Now, you know that a register is nothing more than a D flip-flop at this point, but you always think, we never use like a D flip-flop alone anymore. It's always in groups of 8, 16, 32, 64, etc. Okay? When we go over to memory, what happens is that we use a much simpler storage element to store 1 and a 0 so that it's smaller. Okay? So we can pack more of them on chip, and we give up some of the capability, stuff like the reset and enable and stuff like that. Okay? So that's where we start talking about the difference between storage using D flip-flops and storage using memory. What we do in the first part of this chapter is we define some terminologies and the basic block diagram of what a modern memory system looks like. And then what we do is we move into different types of memory technology, but the technology that we're always going to focus on is semiconductor. Okay? Semiconductor memory means we are going to use integrated circuit manufacturing processes in order to store the 1s and 0s. This is not necessarily focusing on things like a tape drive or a hard drive, and that's it. Okay? Semiconductor memory is the majority of memory that we see if you just look at raw bits, okay? And that has to do with, there's memory systems on microprocessors, okay? Hard drives are still used, but they are being placed with what? Solid state drives. Solid state drives move back to storing information with semiconductors, okay? So what we do is we just go through kind of an exercise of looking at the different technologies that have built, that are used to do semiconductor memory, and the primary emphasis on it is to just get a feel for how do they build these systems and what are the terminologies, what do the acronyms stand for, okay? All right. So here we go. We are going to start off by drawing a picture of a memory system, okay? And when we talk about a memory system, we are going to draw a little block diagram that looks like this. Okay? So we're going to have this memory system, and it's going to have some inputs and outputs. Okay? When we think about this memory system, we are going to start by doing a memory map model, which is kind of this somewhat detailed block diagram or logic model for what's inside of the memory. Okay? So the first thing that happens that's in the memory is what we call data. Okay? So you're going to have data that sits within the memory, but you're immediately beyond the bit level. Okay? You're not making memory systems necessarily anymore that access 1 bit at a time. It's always going to be data words. So it can be a byte, a nibble, a byte, a word. And so what we do is we always start off by saying the data is equal to, it's actually called an n-bit data word. Okay? And so whenever you have the terminology like it's a nibble, that's 4 bits. It's a byte, that's 8 bits. Then you go, they used to say it's a word, which would be 16 bits, and then they got to 32, and they're like, what do we call a 32? And you go, well, it's a 32-bit word. And then at 64 bits, it's a 64-bit word. So the term word starts getting used kind of across the rest of the sizes that you see in the width of data. Okay? And so if you think about this, what this is going to look like is you're going to basically come in here, and you're going to have 8 bits, and you're going to have a least significant bit, 1, 2, all the way up to the most significant bit, which is going to be called n minus 1. And the reason I say that is because if it's an n-bit data word, you are going to have the positions within the n-bit data word assigned just like positions in a binary number. Okay? So if this was a byte, if this was 8 bits wide, you would have position 0, 1, 2, all the way up to 7. But we would still call it an 8-bit data word or a byte wide. Okay? Now, when you start building up this memory, what you do is you take a whole bunch of them and you start packing them in here. So you basically build this array of memory, and it really looks like this. So when you build these things up, it really does look like this kind of very regular array of storage cells that are implemented in Semiconductor. And what happens is that they all have kind of the same addressing scheme, and for a particular memory, they're all going to have the same n-bit data width. Okay? And you sit there and you start immediately going, well, how am I going to differentiate between each of the words? You start doing that with what is called an address. Okay? And here's what ends up happening. If you come alongside, one of the ways that you do a memory map is to the left of this little array that we have, you're going to list its address. Okay? You are going to start with 0, as you might suspect. And what you're going to do is you're just going to list unique addresses all the way up to the end of the array. Okay? Now, when you talk about the depth of a memory, you're talking about the number of unique locations right here. And we actually give this a little symbol, which is M address locations. Okay? So if you started counting at 0 and you went up and you said, well, I have M unique address locations, this would actually be M minus 1. Okay? And this is how you form this array, which is going to be this little thing that has all this information in it, and it is going to be called an M by N memory array. Now, why is that important? It's because this starts getting to what we call the capacity, which is the number of bits, if you don't specify anything else, in the array. Okay? So we sit there and look at this thing, and it's like, well, okay, it's pretty simple. Let's just say that I came along and I said, hey, I have a data array, or I have a memory array that has n is equal to 16 bits. Okay? That means it's 16 bits wide. You store information 16 bits at a time. Okay? And then M would be equal to, let's say it's 256, and this would be 256 address locations. And if I asked you what's the capacity, you would say something in bits. And so this would be M times N, which is equal to 256 times 16. And let's just take a look at some of these calculations. Okay, so I come along, and I'm going to do this. I'm going to bring up my little calculator here. Pop, 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 pop. So I got my calculator. And we're doing some advanced math here, folks. 256 times 16, bada bing. You get this, 4096. And that's bits. Okay? How's that feel? All right. Have you ever heard of anybody? Okay, let's do another example. Just another silly example. And this is in bits. It's in bits. Let's say that I had another example where, I don't know, n was equal to, what's a width of a memory system that you guys use today?
8 bits, like per byte.
8 bits? So like your computer. When you talk about the DRAM in your computer, what's the width of it? 64? Okay. So n is 64. That means that the information is stored in 64 bits at a time. What kind of, I don't even want to get started with how deep these things are, but let's just say you had m is equal to 1024. Okay? And I wanted to know the capacity. Okay? Well, I could come along and say that's nothing more than m times n is equal to 1024 times 64, and I actually have to pump that in my calculator. So I'm going to get myself a 1024 times 64, bada bing. And I get 65536 bits. Okay? What if somebody came along and said, how many bytes do you have in there? The way that you do the byte calculation is when you talk about m by n, it's always in bits, okay? Because you care about the actual capacity is like how many ones and zeros can you actually store? But then sometimes people go, yeah, I'd rather talk about bytes, like how many bytes of information can you store? And in that situation, what you do is you really just divide the capacity by 8. And that doesn't even account for if this was 24 bits wide, you would have like 3 bytes and then for each address. And you could calculate it some other way, but it's like, who cares? Just divide this thing by 8. So if I wanted to come back to this and I wanted to say, all right, I want to know what this guy is in bytes, it would be 4096 divided by 8, and that would be 512 bytes. If I wanted to know what this guy was in bytes, I would take 65536 divided by 8, bada bing. It would be 8192. Okay? Let me ask you a question. When you talk to other engineers about the size of your memory, do you ever say, my memory is 4096 bits? Or do you ever say, mine is 8192 bytes? Does anybody ever talk like this? No, negative. What do you say? You say megabytes or kilobytes or stuff like that. So if I was talking to somebody else, I would say that this is 8K. Okay? I would say that's 8 kilobytes of information that I can store. Notice that 8K is actually 8,000. Do you notice a difference between these two? They're different numbers. It's just that this is the way that we talk. Okay? This is the way that we talk, and this is the actual information. So when somebody says to you, hey, I've got 8K, they really mean they have 8,192. Okay? It starts becoming further and further off the higher the numbers you get. For example, if somebody said, how many bits do you have in your memory? You would say to another person, I have 64 kilobits. Look how far that guy is. Like that's not even, like only one of the numbers matches now. The 6 matches, but the 4 went to a 5. So what happens is it gets further and further off, but it's fine. As an engineer, what you need to keep in mind is that the way that we talk is a shorthand, okay? So the capacity, nobody's rounding these bits off. It's not like somebody built an 8192 byte memory system, but just because we call it 8K, they went and deleted 192 bits. The bits are still there. So it's up to you to keep that in mind, the way that we talk versus the actual capacity. Roger that? Okay. Now, another thing that is fascinating, okay, is how do we get information into this thing? Well, if you think about this right here, if I drew this as like a block diagram, I'm going to like let's say that I actually had a VHDL entity. I will have something that will be the data, okay, and it is going to be as wide as the data bus. Okay, it's going to be n bits wide. That's it. And let's just say for sake of argument that we're simplifying where we can transmit information back and forth. When we give this thing the address though, okay, do we give it M? Is this M bits wide? The answer is no. Okay? What we are going to do is we are going to give a binary code for the address. Okay? So when you ask how many address bits are there in a memory system, it's actually not going to be M. It's going to be the binary code that represents the integer M. Now how do we find that? Well, this is where you go 2 to the n. Now this is a big, don't get confused when I say n, because almost everything's called n in digital, right? It's like we finally introduced m, but we love n. So what we do is, n in capital is the width of the data bus, the width of the memory, but little guy, remember little n? Well, little n is the number of bits, and it's always the number of bits. So, if I think about this, let's say that I just made a table called n, and I had 0 bits, I had 1 bits, 2 bits, 3 bits, 4 bits, 5 bits, bits. And I wanted to know what the number of unique addresses that I could locate or have in my code that was n bits wide. How would I calculate that? 2 to the n. Okay? So 2 to the n. If I had 0 bits, this is kind of a funny one. If I had 0 bits, how many unique addresses could I have? You could have 1, because it's only one location. That's it. You don't get to change it. So you actually do have one there. But we don't make any memory systems like that. So let's forget that. Let's forget that. If I had 1 bit, how many unique addresses would I have? 2. Okay, that's pretty cool. So my addresses would basically be, I'd have a memory system that looked like this, and I'd have 0 and 1 as the 2 addresses that popped in there. Okay? Okay, well, let's keep this going since it's so fun. What if I had 2 bits? I'd have 2 to the 2. I'd have 4 unique addresses. So my system would now look like this. I'd have 0, 1, 2, 3. Yes. Yes, they're the binary code. All right, that's pretty cool. Let's go to the next one. What does 3 bits look like? I can address 2 to the n unique bits, so that's going to be 2 to the 3 is equal to 8. Now what does my system look like? Now it's almost to the point where I can't even draw it anymore. So my m would be 0, 1, 2, 3, 4, 5, 6, 7. Okay? And the binary codes would be what? 0, 0, 0, 0, 0, 1, 0, 1, 0, down to 1, 1, 1. Okay? You notice that the number of address lines that we pass into the memory system is significantly less than the number of bits we have. Now, we can always take the number of address lines and calculate the number of unique locations, or m. So if you think about what we did is we said 2 to the n is equal to m. Would you agree to that? Where n is going to be the width of the address bus. M is going to be the unique locations that I have in my memory array. If I told you that m was 1024 and this was 2 to the n, oh yeah, what would we do? Holy cow. We got the numbers over here, but the solving for thing variable, the jig, is up in the exponent. Does anybody remember how to do this stuff? Something like a logarithm. Remember that thing? All right. So I'm going to take the log of both sides. And the reason I do the log of both sides is because if I take the log of something with an exponent, it brings the exponent down. So I have the exact same. These two are equal to each other. It's just a manipulation of logs. And then this becomes log 1024. And then if I want to solve for n, I simply say n is equal to log 1024 divided by log of 2. What's that end up being? Well, let's figure it out. A lot of logs. So log of 1024 is like 3.0102 blah, 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 blah. Log of 2 is equal to 0.301 blah, 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 blah. So what does this end up being? It's about 10, right? So I have 10 address bits. Let's think about that. Let's think about 10 address bits. If I continued this down in my capacity table right here, I'd have to squeeze in 6, 7, 8, 9. Let's see where it goes. 2 to the 4 is what? 16. 2 to the 5 is 32. 2 to the 6 is 64. 2 to the 7 is 128. 2 to the 8 is 256. 2 to the 9 is 512. 2 to the 10 is 1024. Bada bing. Not too bad. Now, not too terribly difficult. All we're getting at is that we are going to have a system that has a block diagram that looks like this. You are going to bring in address, and it is not going to have m address lines. Okay? It is going to have little n number of address lines, and that's going to be equal to what? Log of m over log 2. And then you're going to have a data bus that comes into here, and this is going to be capital N. And if somebody came along and said, what's the capacity? You would have to find what m is, multiply by n, and that would give it to you in bits. And if somebody said, I want it in bytes, you simply do m by n divided by 8. Okay? How's that feel? All right, not too bad. Not too bad. And it's important to think about the way that we talk also. Okay? Should we do an example? I guess we just did. How could we, let's see, what's a good example? I have 16 kilobytes of memory, and it's an 8-bit wide system. And I want to know how many bits are in the address bus. So somebody walks up to you and says this, I have 16K bytes, and it's 8 bits wide, and they want to know how many address lines do you have. So it's kind of interesting because, okay, well, it's not a big deal. Since they gave this to me as the data is actually 8 bits wide, that handled the bytes. So what that means now is that my address needs to have 16K unique locations. Does that make sense? Each location will hold 8 bits or a byte. So the question then becomes, if this is kind of what m is, we need to find out what little n is. Now, here's what we got to think about. People are talking saying 16K, but is it really 16K exactly? No. To find out what it is really, you could actually put it in a spreadsheet and actually calculate every possible number, or we could put it in this logarithm and we could figure out what it is using 16K and then round up. Does that sound feasible? Okay, so let's do that. If I come in here, what I'm going to have is I want to put n is equal to log of 16K, and I know this isn't accurate. This is taking into consideration that people are saying 16K when it's actually 16 something. So then I'm going to do log of 2, and does anybody have that calculated?
13.966.
13.966 bits. Let me think about that. Let me check your math there. Correct. Now you go, dude, what's a 0.966 bits? What's that have to do with anything? That is just nothing more than the accounting for the fact that it's not exactly 16,000 address locations. That's just rounded down. So if I rounded this up, or rounded that up, I would say, you know what, the n is really 14 bits. How do I check whether that is accurate or not? I would say, what is 2 to the n being equal to m? So I'd come over here, and I would say 2 to the 14 is equal to, it is actually equal to 16,384. Okay? Does that make sense? So it's like, okay, that does work. That absolutely works. The number of address lines is equal to 14 bits. This is very important because somebody came up to you and said 16K. Now I want to ask you a question that will trip you up on the homework problems. Happens every year. First of all, what I just said, that trips people up. What is the capacity of this system? Here's what most people do. Oh, dude, no problem, man. Capacity is 16K times 8. Let me do that math for you, Holmes. 16,000 times 8. Bada bing, 128,000. Give me my money. Wrong. Okay, now why is that wrong? Because the capacity is not, when you do the calculation, the capacity is not 16K exactly. 16K is how we talk. So the capacity is actually going to be 16,384 times 8. And that now is going to be equal to 16,384 times 8. That is actually equal to 131,072 bits. You see the subtle difference there? The way we talk is not the way we do the math once you start getting to these big numbers. Feel good? Okay, okay. Life is good. Life is good. Another couple terms that we want to kind of define when we think about this whole memory map system or the memory system is this. Okay? When we move things into memory, okay, so this is my memory. So I have an address, I'm going to have data. When I put information that way, okay, it is going to be called a write. When I take information this way, it is going to be called a read. Okay? Very important to use those terms. The reason those terms are defined so explicitly is because if you are taking a digital logic course, you probably have also taken an embedded systems course, or you will take an embedded systems course. And they define terms load and store that refer to moving information in and out of a memory system in a microcontroller. These are not the terms that we use for moving information in and out of a memory system. Okay, these are actually instructions that a microprocessor can execute. So don't use the term load and store because those are reserved for something else that will come later. What we talk about is reading and writing from memory. When we read and write from memory, we always do it at the n-bit word level. So I'm going to write 8 bits to memory. I'm going to read 8 bits from memory. I'm going to write 64 bits to memory, etc., etc. Okay. Feels so good. Now let's define just a couple other terms. Okay? We have 2 categories of memory. One is called volatile and one is called non-volatile. Now you've probably heard these, but what does volatile and non-volatile memory mean? It just has to do with, does it store information when the power is removed? Okay? So volatile loses data when power is removed. Okay, so loses, is that how you spell loses? You can't even see it. Whenever you can't spell a word, you just kind of scribble it. So it's like, does not lose data when power is removed. Okay? Now, what does this mean? Exactly what I just wrote. You have a memory system. Some memory, you can pull the power from it and it stores. Okay? Some other information, when you lose the power, the information's gone. Just to jump ahead using terms that you may or may not have heard of, but what are some examples of volatile memory? RAM? Oh, don't get me started, man. Volatile memory. Examples of this are cache memory. Other examples are, you're right, cache memory. What are some other examples? Don't even start it. That's not memory. It's basically cache memory. Okay, we'll get into the details of that in a second. What's non-volatile? Has anybody, like a hard drive would be considered that? Yeah, tape memory, flash, like a thumb drive. Wow, flash. And we don't even proms. We don't even know what these terms are. That's kind of what comes next when we start talking about the memory technologies. But that's just the big terminology, volatile versus non-volatile. The reason it's important is because memory, the reason we have memory really is to build a computer. And a computer executes instructions. And the instructions that it executes has to be stored somewhere that when you plug it in, it has that information. You don't want a computer that you plug in and then you have to like take something else and load in the ones and zeros. You want to have the computer to have some sort of non-volatile memory in order to boot up from power up. Okay? But volatile memory is way faster. So that's why we use volatile memory once we get booted up and we start running really fast. Okay, the last terminology that we're going to talk about is random access versus sequential access. Okay, and this is where we tend to use the word random access. This is random access memory, or RAM. We use it incorrectly almost exclusively. Okay, sequential access memory doesn't even have an acronym because we hardly ever use it anymore. But random access memory simply means that you can come along, okay, and you have some sort of address. We'll put it right, we'll put it out here. Okay, you provide an address to this puppy, and it will spit back the data no matter what address you give it. And this is very intuitive, the way that we just described a memory system using an array. You give it an address, and guess what comes out? The data. Guess what goes in if you want to write to it? The data. You can access any memory location at any given time. It is random access memory. Notice that RAM has nothing to do with volatile or non-volatile, but this is just another way that computer people talk. When we talk about RAM, somehow it has been linked to to volatile memory, because we call our RAM in a computer RAM, right? Our DRAM, where we store our programs when we're running, is called RAM. And it does happen to be random access memory, but it also happens to be volatile, because when we turn off our computer, it loses it. So we typically start talking about, the RAM in my computer doesn't store when I'm plugged. Well, that has nothing to do with volatile or non-volatile. It's random access, meaning that you can access any address location at any given time. Sequential access memory is actually almost difficult to explain because we don't have a lot of technology that uses it anymore. Sequential access memory would be an example of like a tape drive. So imagine that you had a tape drive, and it's a spool of tape that's like a mile long, okay? And you're like reading right here. Okay, this is how tapes, this is how they look. If I give it an address, and that comes, and it's like, and here it comes, and it cruises by. All the while, I was reading everybody that came in front of it, so I'm reading everything in a sequential access manner. A hard drive is also somewhat sequential access memory. You want to know why? Because a hard drive is a disk that stores information as little magnetic permutations in here, where you go along and you like change the material properties so that it's storing a 1 or a 0. And then what you do is you use this little head and you spin the thing around. So it's spinning, right? So it's like, and then you read it and you're like, and you're reading the thing. And what happens is that you read these bits. They're coming one at a time. So it does have this kind of sequential access strategy to it, okay, or behavior to it. You can jump around, though, more so than in a tape memory. So you could be reading information over here on the outer ring that is sequential, and that's true. But then you can jump to another section that is also sequential. So it's kind of like sequential-ish. Okay, so those are the terms that we tend to use when we talk about memory systems.